Hi, welcome back to my channel. So in my previous video, also about this oscilloscope, the Siglent SDS 1202X-E, one of my viewers said that, well, the video was useful in making a decision about buying a new digital oscilloscope. So in this video, I want to make a remark about this oscilloscope that might be useful for somebody. And it is the fact that compared to the 4-channel version of the same line of oscilloscope, Siglent, this oscilloscope does not have a Bode plot functionality. So the Bode plot functionality, I'm going to discuss it in a second, but it allows you basically to connect with a signal generator, but it must also be a Siglent signal generator, and it allows you to create Bode plots. Okay, so it's not a big deal that this does not have it. In fact, I will show you how to do it with any oscilloscope. I will use my analog oscilloscope to create the Bode plot, basically to illustrate that this can be done with any kind of oscilloscope. But if you have a 4-channel version of this and a Siglent signal generator, you can have a nicer integrated thing, basically. So to illustrate this thing, I have here a little circuit that I'm not going to show you physically, but diagrammatically, basically. So there is a signal being a signal generator here, and it's coming out of channel 1 of my signal generator. And the signal is going through a capacitor. Here doesn't matter the capacitance, but it's about 4 nanofarad, then an inductor, and then a resistor. And the point is that when you have a capacitor and an inductor in series, well, it happens at the resonant frequency, so their resonant frequency, that basically the two cooperate and they become basically a short, so there is no resistance offered by these two together. And so at that specific frequency, the resonant frequency, this point here, measured by channel 1, so basically the signal at the input, and this point here, measured by channel 2 of the oscilloscope, will be basically identical. Okay, if we use the math function channel 1 minus channel 2, we will see basically the voltage across this point here and this point here, and again at resonance this will go to 0. Okay, so that's the basic thing that we have here, and that's what we are having at the moment on the oscilloscope. So the yellow line in the signal at input, so it's 2 millivolt peak to peak for divisions. At the moment, I don't know if you can see, but we are at 500 millivolt per division. Anyway, sorry about the focus of this camera, but it is what it is. And on the purple line we have this point, channel 2. Okay, so at the moment it is, the focus is better this way actually. So as you can see, at the moment channel 2 is a little bit lower than channel 1. So we are not at frequency. The two, the capacitor and inductor, are offering some impedance. And the white line, which is channel 1 minus channel 2, is indeed not a flat line. So it's not 0. Okay. At the moment, notice we are at 400 kilohertz. So let me try to reduce the frequency a little bit. So, right. So, yeah, we are kind of reducing the noise. It's become the difference is becoming lower and lower. And notice also that the phase between these two signals, the yellow and the purple, is going down. So let me go back to 500 where we were before. We had about 40 degrees of phase difference. It means that, you know, the capacitor and the inductor are doing some phase things, and they are not just a short, otherwise the phase will be 0, right? So now by going down, the phase is going down as well, and we will be basically at resonant when we are at phase equals 0 degrees. So now we are at 100 kilohertz, as you can see here. Let me go down a bit more. So the phase now is 1 degree, so let me go down a bit more. So the phase is just above 0, so let me just decrease a little bit more, a little bit, so we are at 8 kilohertz, yeah. just above 0, as I was saying, and so let me decrease it just a little bit, and I think, yeah, basically here it were resonance, right? So you can see a completely flat line, and the phase is kind of 0. Okay, so we basically discovered this type of things, I mean the resonant frequency manually, but the Bode plot is basically something that allows you to plot response, in this case the yellow line here that we care about, so this difference, over frequency. So we would, the Bode plot here would plot something like 0 hertz and let's say 1 megahertz, and it would be something like this, right? So in a very crude way, this would be the graph. So on the horizontal line we have a frequency, and on the vertical axis we have this yellow line, and the minimal point of this line would be our f, the resonant frequency that we know is 77 kilohertz, right? So yeah, if I had the four channel version of this oscilloscope, I could basically connect it to through USB, some cabling, and it would produce this by itself. But let me show you how you can do this manually, and I'm going to use in fact this analog oscilloscope. So the basic idea here is to use the signal generator. Instead of producing manually moving the frequency around, I'm going to sweep the frequency. So let me sweep, let's say, from I don't know, 0 hertz basically. Sorry, sweep time, it's all right. So how do I cancel here? Cancel. So the sweep time 10 milliseconds, fair enough. So the start frequency 1 microhertz is fine, so it's basically 0, right? And the stop frequency, let's put it 200 kilohertz, for example. Right, so now the signal generator is sweeping, so it's doing this 100 times per second. And so I'm going now to also to channel 2 to produce a square wave that happens 100 times per second, right? So this basically will inform us so that the square wave rise when the sweep is starting, okay? And it's perfectly synchronized with the sweep on channel 1. So let's go back to channel 1. And so what I'm going to do now, I am basically connecting channel 2 to channel 2 of this oscilloscope. So here, channel 1 to channel 1 of this oscilloscope, and I'm instructing by this button that I have here to use the external trigger of the oscilloscope, which is in fact connected by the square synchronization signal that comes out of channel 2 here. And so this is the result. You see, this is the Bode plot that we have. So let me so in fact the signal that we get is this, right? So we start with low frequencies, and there the difference between channel 1 and channel 2 is high, as basically we expect from the diagram that I made. We reach a minimum that is going to be our 77 kilohertz, and then it grows similarly to this thing, right? So if I set the division here of the time division to 1 millisecond, we get exactly in the screen here we have 10 division. 10 division of 1 millisecond means of course 10 millisecond, which is the sweep time. So here we basically have 0 hertz, and here we have 200 kilohertz. And so basically we have about 20 kilohertz per division. And indeed, as you can see here, the minimum is visible at about in the 4th division. So it's about the 77 kilohertz that we expect. So I think it's pretty nice that you can visualize this on even a simple analog oscilloscope. So what I did is basically just connect the two channels again, and this oscilloscope has this functionality of basically I can select add and invert the signal basically to compute the difference between channel 1 and channel 2. If your oscilloscope does not have this basic functionality, you can just use one channel, in fact, and connect it directly over here instead of having to do the subtraction of channel 1 and channel 2, right? So that would be even simpler way of doing things. And then you can have your Bode Plot function. But again, it would be nice to have it completely integrated, since I happen to have a Siglent signal generated by Siglent. But unfortunately, it's not available on the two-channel version of this oscilloscope. I think it's just a marketing restriction, right? Because the hardware, I mean, we can see the phase, we can see the amplitude, so there is no reason why this oscilloscope should not be able to do that. But okay, it is what it is. And anyway, I hope this video was interesting to you. Okay, I see you next time. Bye bye.